edition of the weekly hangout, LunarCubes, 14/08/12. That's today. Today's topic is going to be a progressive autonomy in the spacecraft to come. And my co-host and guest speaker today is Michael Riley. Okay, and let's get going. Michael, back to you.
Thank you, Abraham. It's good to be back on the air. I'll just share these slides. Today we're talking about autonomy, the control of the infrastructure that's going to make up the deep space information systems associated with the LunarCubes and the lunar network. The idea... Hide something there. Very good. So this is some work that we've been working with the LunarCubes effort, along with Abraham from Fletcher Engineering and also Russell Cox. The lunar networks, take a look at the vision. We've talked about this several times in our previous Hangouts. It's an expanding web of service providers providing a variety of services out in cislunar space. And the idea is to explore and develop the moon and develop the technologies that will allow us to move beyond as well. Before I go on, Abraham, are you able to see these slides well?
Yes, the slides are good.
Okay, very good. So there, if you take a look at some of the different architectural elements of the lunar network's vision, the services being provided, that's analogous to the service-oriented framework that we are developing on the ground and use commercially today. That's our lunar cloud. The connectivity is the lunar web, and the nodes in this network are the spacecraft, which can be cube-based spacecraft or even conventional-based spacecraft as well, depending upon the actual needs of that architectural element. Where you envision, one thing Abraham likes to remind us is that the nodes can actually be subsystems of spacecraft as well. For example, if you have multiple sensors on board a spacecraft, each one of those could have its own node address that you could connect to as time goes on. The idea behind developing deep space, one theme that we have is that the concept of what is close to the Earth expands as time goes on. At one point, it was, well, we pretty much take for granted a lot of the things that we have in low Earth orbit now. We have several hundred spacecraft that are operating around the Earth and providing a lot of information and services every day. And that has grown to involve things in higher orbits, the Molniya spacecraft, for example. And then finally, we've gotten a lot of use out of the geosynchronous space as well. Another notion is that, take for example the communications network that we've developed around Mars. Originally developed in an ad hoc basis, but now we have spacecraft which are providing a communications network that the robots on the ground and spacecraft that arrive around Mars are providing services to each other. So the idea behind developing deep space, our own vision for the lunar networks, it's service-focused. You can start to rely on the network providing services to you, so you don't have to bring everything with you for your particular spacecraft. This enables specialization, which is important for putting together an efficient use of the resources that you have, because it still is expensive to get to space, and you want to make sure that you get the best bang for every gram that you get out there. There's a trade-off between complexity, flexibility, and capability. The idea that I'm getting at behind that bullet point is that you opt for a more complex solution. In essence, the network itself is more complex, but you gain a lot of capability by trading off different services to the space to the lunar network itself. For example, if I have a big spacecraft with a big transmitter on board, maybe with my smaller cube spacecraft, I don't have to plan on communicating directly back to Earth. I just communicate directly with that big transceiver that I have on that neural networks node. So as time goes on and as you add assets, you expand the infrastructure, and this gives people a better way to apply in a focused way different investments. Well, it really lowers the cost of creating new technology. It's cheaper to get things out there, and one important point is that it's inherently a multi-spacecraft solution. Now, one point about having an inherently multi-spacecraft solution is that you have to figure out how to control these things. And today, controlling spacecraft is a very hands-on process. You're really focused on keeping that one spacecraft alive. You have some automation on the ground, you have some autonomy on the spacecraft, but still, it's really focused. And you have a lot of people in the loop in different places. So, who's going to broker the services in our infrastructure? You have all these nodes providing different services. Who's going to be handling the requests for the different services? Are you going to have people who are commanding one spacecraft, sending commands up to that spacecraft, which then bounce those over to another spacecraft to request the services? Maybe not. Are you going to be doing some of that on the ground? Are you going to have say in the ground segment, I'm one person with their ground computer talking to another person's ground computer to reserve the services of the things that are remotely deployed. How are you going to conduct those transactions? Are you really going to want to have people in the loop and have everything planned out in advance? I've been told that even with the limited autonomy that you have on board the Mars rovers, at one point it took about 230 people to drive the Mars rovers, a few meters at a time. So that's a huge investment to remotely control these remote assets. Do you really want to have humans in the loop driving up the costs, particularly if it's a CubeSat? That's a big question and a big stumbling block for some advanced requirements. Complex goals are going to require complex functions, and you're going to have advanced control capabilities to drive down the cost of controlling that entire network. You're going to have a lot of capability, ranging from ground-based automation and autonomy, and eventually getting the spacecraft to do that themselves. So to achieve that resilient behavior, well, get back to that near-Earth expands theme. Advanced capabilities and synthetic services require on-site decision-making if you want to be both reliable and resilient. Okay, deep space provides some pretty big challenges: bandwidth and latency, and also human interaction is very expensive and dear for an asset that's been deployed to remote space. You need to move from automation, things happening like clockwork, to autonomy, where you can deal with things that aren't on the schedule. Now, people have been looking at spacecraft autonomy for some time, and people were trying to figure out how to characterize different levels of autonomy, and people looked at that for quite a bit over the past few decades, particularly for the International Space Station. Folks were trying to figure out, well, how can we control such a big, complex entity as the space station? And people looked into, okay, what sort of automation do we need? What sort of autonomy do you need? Is there some way that we can avoid keeping and employing an army of people on the ground just to keep the thing moving and acting? And there you had people talking about different levels of autonomy to try to fix their ideas and provide a framework in which they could understand how to make something more autonomous. One thing that you see in this particular levels of autonomy, that was put together by John Anderson of NASA back in 1984, you start with something that executes external sequences, commands step by step at pretty much the lowest level. That's where you're commanding everything. Everything is going by pre-specified rules, down to something where you're actually delegating some responsibility to the spacecraft system itself, where the spacecraft starts to have some choice. And one thing that you find is if you're operating on commands and rules only, everything has to work right, or you have to have a pretty complicated rule set that takes into account the different contingencies that can happen. And those systems, well, fundamentally they're going to be brittle because at some point you're going to be applying the rules wrong. And the history of spacecraft faults and failures is replete with examples where the state of the spacecraft or the state of the commanders, the people on the ground commanding them, don't have things quite right, and they cause a huge problem. Which is, one big example of that might be the SOHO spacecraft, whose internal state of its angular momentum wheels was in a state that nobody really appreciated, and the commands were sent to the spacecraft to try to right itself. That actually caused more problem and caused the spacecraft to go tumbling out of control, and they lost contact with the spacecraft for about 3-4 months until the spacecraft rotated around and the sunlight fell on its solar panels again. However, they were able to recover the spacecraft. If the spacecraft had some autonomy, if it had some of its responsibility delegated for its own health and safety to itself, it has a limited amount. But if it had been able to take a look at those rules, at the commands that were coming to it, and say, hey, these commands don't make sense for the state that I'm in, then you might have been able to avoid that fault with the SOHO spacecraft, and you might have not run the risk of serious harm. As it was, it just froze everything on board the spacecraft, and they had to spend about a month or two after losing contact with it for about 3 or 4 months to bring it back up to speed. So these are big issues. Now, one way to, or one approach to looking at autonomy, if people have a hard time delegating that responsibility to spacecraft, and for good reason as well. If a little thing goes wrong in space, there's nobody around to really fix it. And really the only connection that you have with most remote spacecraft is that radio link that you have with them. So people design they design their control strategies very conservatively and very carefully to try to make sure that they maintain that radio link and that every contingency is accounted for, which in some sense is a losing game, because you're not going to be able to count. You're not going to be able to catch every contingency. New things do happen from time to time, and it's mainly because we have a lot of experience in space that we have been able to catch most of the we think you're able to catch most of the errors and problems that can occur. But every so often we still do have failures. So if you're trying to build confidence in a particular system, in particular a control system, or something that's supposed to take over some responsibility for its own health and safety, that in itself is an architectural problem. How do you gain confidence in something, particularly if it's a big spacecraft, which requires a large investment, community from a defense or a scientific community investment, hundreds of millions of dollars, perhaps even $1 billion. That's a big step, and so people are naturally going to be conservative, and you make very incremental steps in autonomy and automation, which is one of the neat things about the Cube spacecraft, is that it lowers the cost of that innovation. But one idea to look at developing some confidence with that delegation of responsibility to spacecraft was something called progressive autonomy, and it was developed. It was one of the places that it was developed and worked on was at Goddard Space Flight Center with Walt Truskowski and Chris Ralph, and that was a group of people that I did a lot of work with during the time as well. Their idea was to use a software construct which was somewhat popular at the time, the agent. With an agent, you delegate some task to a piece of software that then acts in your stead to perform that task. The commercial world has pretty much moved on from agents to services. Moved from an agent-oriented ideas over into service-oriented, because those are a bit more easy to control and configure and use. But agents were a useful way to talk about some of the problems that you have in controlling different systems. And the idea behind Truskowski and Ralph's notion of progressive autonomy is that you would slowly and incrementally build up your confidence in different control systems by trying them out on the ground first, and then as you gained confidence and capability with your autonomous agents, you would migrate those from your ground system up into the deployed system. And that was one of the interesting things about the agent, is that one of the ideas behind an agent was that you had an ability to migrate it from one system to another, sort of like the idea of or the capability that you have with virtual computers to move them from one piece of hardware to another. With an agent, you're able to move that agent around from one environment, from one operating environment to another, as long as you met certain properties for being able to run the agent. So the idea here was to buy into that ability to migrate agents from the ground up into space. And so you would start out up in the space-based with an elementary system that could run the agents, but would not necessarily have complete responsibility. Perhaps it was more like a daemon or something like that at the beginning. And then as time goes on, as your ground-based agents became better, you could then migrate them up. So let's take a look at this in a little more detail. Starting with the ground, the idea is that you would have a community of domain specialists. These would essentially be subsystem agents, or agents designed for a particular task. One thing that you could have is that, for example, if you had, say, a group, multiple groups of scientists using the spacecraft, each group of scientists could provide its own agent for its own mission. Its own sub-mission, if you will. If one group is looking at the mountains of the moon, and another group is looking at the lowlands, or another group is looking for, say, creep materials, they could each come up with their own agent, which would encapsulate the questions and observations that they wanted to make, and you could actually program that in and run that in your community of agents on the ground, and then that would communicate essentially commands and requests for services up with the spacecraft. So that's where you would develop your agents and get some experience with your agents as well. You could have them communicate with less capable agents, or even just the spacecraft itself, through the various communication networks to get out to the final spacecraft. And in a lunar networks view, you'd have multiple hops, for example, as you go from one node to the next. So you develop your agents on the ground, maybe you even run them on the ground, and an interesting thing that you can do is that you could also have, for example, shadowing. The agents could shadow the system. For example, you receive information on an ongoing basis from the spacecraft and the different nodes of the network, and using more conventional methods. And you could have your shadow agents, which sort of watch over the shoulders of, say, the human controllers or the automation that's being used. And so in that way, you could have agents that could learn, or you could just simply test out to see what they would do in different situations. So those are some things that you could actually do on the ground. And because agents naturally lived in a distributed environment, you could actually have your agents working from different user sites. and operate in a distributed manner as well. The agent, moving from the agent development side at the users, then you have the ground-based autonomy section. This is where you have your control operations environment. This is where you have your ground segment involved, and this is where you would actually deploy. A user could deploy their agents to get some of that shadowing. Some of that shadowing exercise for some of the training exercise as well. And so you could actually migrate your agents from, say, the user-based development environment out to the more operational environment, but still on the ground. And this is where you could actually gain a good deal of experience with how your agents actually work in an operational environment, for example. So you've gone from so you can start with your ground-based operations environment with its automated support, augment that with agents, which would provide a limited amount of autonomy for particular tasks. And as you gain experience with the agents operating on those individual tasks, for example, working with different checking out agent independence and the non-deterministic behaviors as the system evolves. Once you've gotten some experience in that sort of operational environment, then you can take the agent, and once it's all checked out and you're confident with it, you could send that agent actually into space and deploy it. And then you have your agent operating system, and this could be sort of like the final point where your agent would migrate to and would actually operate in the agent-based environment associated with the spacecraft. And there's some interesting things that you could do with that sort of architecture as well. The agents could rest and work in a protected environment away from any critical systems on board your remote spacecraft, or if you're confident, or the cost and risks are acceptable, you could actually have the agents control the spacecraft as well. Again, the progressive notion, the progressive part of the progressive autonomy, is that you would be building up your confidence in your agents and in the entire architecture as time goes on. And one of the things that this allows you to do is that you have a progressive way to first start with start with building up your agent-based autonomy in the sandboxes with the user. Then you move that into an operational environment, test operational environment, and then finally move them into space and have them start to control and help provide the services that we're talking about. And that's where you get the connection with the lunar networks. Because when we say, okay, what is a transaction going to look like? Well, the agent-based systems are all about transactions, about how the different agents interact with each other, and how the agents actually provide services to each other as well. And you can even, an important part of an agent-based architecture is the notion that it can act as a delegate, or it provides an agency for different aspects of the user environment. So if I'm a person who is interested in particular conditions on a particular set of moons on the mountains on the moon, then when those conditions occur, the agent can wake up, it detects those, traps that information, and then prepares to send it back via the network. These are some of the things that you can start to do with an agent. An agent can actually be an economic advocate as well. We talked somewhat about how you're going to have the different services interact with each other. How do you come up with a pricing scheme? Agents can also provide a way that you can do bidding and negotiating even in an autonomous manner as well. One thing that Truskowski and I worked on was having a set of remote agent advocates essentially bidding on limited downlink bandwidth for a group of different science goals. And so that way, you would have, well, what would happen is that you would have a number of different science agents which are looking at data on board a particular spacecraft and engaging the importance of that science data against the resources being allocated to that particular part of the science team. And so you could have 6 or 8 different science goals implemented as agents bidding for downlink bandwidth. And the guys, who find life, they're going to bid everything and get some space on the telegram back home. So some problems with the agent-based approach and a progressive approach. You can't, as we've learned from some of our aviation accidents that have been tied to cockpit automation and autonomy, it's hard to have 99% autonomy. If you're going to require that a person has to step in that 1% of the time, they could be napping, they could not be trained well in that 1% contingency. So if you're interested in reducing risks, dealing with contingencies, that 1% there is going to be a big problem for you. So for an autonomous situation, you sort of have to have all or nothing in order to have confidence that the system is going to be workable. So that human factor that comes in, that's really a critical link. And if you're going to come up with a solution that's going to be resilient and autonomous, you're going to have to aim for 100%. Now, how do you discipline? Another question is how you discipline and integrate the different agents and behaviors. And also, how do you manage the system as it evolves and learns? And for that evolution and training, I'm talking about the people, I'm talking about the agents, and I'm talking about the non-agent-based parts of the system as well. There's an evolutionary theme here, and one point to recall is that a lot of what we're talking about with current spacecraft control, you're remote commanding, you're setting up rules, and in automation, you're setting up a rule-based system with some limited on-site decision-making, and that goes back into choice. So there's this notion, there's this idea that you have to follow the rules, and when contingencies arise, you start to go after and start to go through your nets of rules to find out what the right decision is going to be. Sometimes you're not going to have enough rules, and you need to allow the system the flexibility to be able to make that on-site choice. Agents provide a way to put some of that in there, but they're going to be difficult to discipline and actually adapt to the system. So you need something else in there. You need a methodology for bringing these agents together and having them be able to put their behaviors together in a balanced way. And a lot of work was done that at Goddard Space Flight Center and other places over the years. And one of the things that we discovered with Stephen Curtis in looking at small spacecraft systems and networks of spacecraft was that you're going to have to balance off the number of rules you put into the system with the choice that you allow to the system. If you go with all rules or all choice, both of those are going to be unstable. If we haven't mentioned it before, rules are fast. Once you make the recognition criterion for executing a particular rule, you've met the rule, you've met that predicate for the rule, and then you just fire off the action. Choice generally requires some deliberation, and that's a bit more expensive. One thing about rules is that, well, if you have a lot of rules, that can provide some inertia into the system, whereas if you're allowing lots of different choices to be made, that tends to aid innovation. But too much innovation, again, is unstable. You need a balance. Agent technologies do not provide that particular balance. It's just not part of their system. You have to add something else. And we came up with that sort of thing with the synthetic neural system that Steve Curtis and a team of us at the NASA Goddard Space Flight Center put together. Getting back to the ground segment and its part in the lunar networks, autonomy is going to be necessary, both ground-based and space-based. And and I think that our work with Truskowski and progressive autonomy is a great way to start to build confidence in autonomous systems. You start by increasing automation. You build up your experience in the ground-based systems. Then you start to migrate that behavior out to the space-based elements themselves. And an important thing that we haven't gotten into very much is that you need to have a disciplined and balanced evolution so that you're always balancing the rule systems that are underlying the control with the different choices that you're delegating to the remote systems themselves. So that, in a nutshell, is progressive autonomy. And again, the fundamental idea is that you build a system that allows you to migrate behaviors from an environment where you have a lot of control, a lot of hands-on capability, to the remote place where you don't have that hands-on capability, but you do it in a way that is balanced and provides you with confidence, as much confidence as possible, every step of the way. Right? So that concludes our talk about progressive autonomy.
That was extremely good. Thanks for bringing up some of the old art of the agents, which we don't talk about, but I think this is a very relevant and very useful member of the architecture. Thank you for that.
You're welcome. Thank you.
Michael, now can we see you on the camera? So I have a couple of questions to go with that. So, yeah, where is it? Okay, I'm clicking you. Okay. The question I had was, can you identify about 3 to 5 agents that may be relevant in our LunarCubesat?
Some of the agents that we came up with when we were studying the frontier system for DARPA's F6 project come to mind. Some of these involved just that bidding that I was talking about before. The idea there was to put a network of services into space, and then you would have different, we weren't calling them agents at the time because we actually had to have some of that integration and disciplining behavior in them. And when you do that, they become a different software construct called a neural basis function. And that was part of a synthetic neural system. But just borrowing the term agent for the moment, we would have agents that would be, whose task it was, say, to detect, they'd be on the consuming side, where they were synthesizing different services together to perform a goal. For example, fighting forest fires, or detecting, or maybe detecting floods or outbreaks of disease, so some signatures of those from space. So you could have those are some of the consumption side agents that you would have. But on the other side, the producer side of the equation, those nodes, those spacecraft systems that were providing a service, they would also have an agent that would be accepting bids for their services and choosing those bids that made the most sense for that particular node. So, for example, we have the communications network that we're talking about, and the big pipes, the high bandwidth communication that you'd have with, say, for example, the conventional spacecraft that would be in their after mission, in their after mission, if you will. Those guys could have an agent sitting there accepting requests for their services from the different cube-based assets, and then once they detected, once they found a set of bids that made sense to them, then they could actually align and execute the actions that would cause those services to be provided. So, an agent-based way of setting up communications on a high bandwidth pipe might be one might certainly be one way. Science agents, for example, like I mentioned that we studied with Truskowski, those things that would recognize interesting things in data that was being taken by a particular on board a particular spacecraft. Rather than, one of the things that we were looking at was that if you had with sensor technologies as advancing as quickly as they are today, you can probably outstrip any downlink budget that you could ever think of with the sensor technology. And so one of the concepts that we were looking into was that would you be able to put a science recognition agent on board a spacecraft and have it get a look at in real time at the highest quality, highest resolution data, and then decide or prioritize which bits to send down first. So one of the things that we always came up with is that people were always saying, well, we want to get every bit that we can. So oftentimes what that meant for the scientists was that they would back off on the capabilities of the science instrumentation themselves. So that, because they say, hey, we can't send back every bit, so we're going to choke down the quality of the science information down to what we can send back. So one thing that we were saying, well, why don't you just run the instrument at full bore the entire time, get the highest quality data, and then have some recognizers in there that select off high quality pieces of that information, send that information back, and then use some software to cut it down to to cut the data quality down to what you were going to propose anyway. So you'd actually come up with a system that had a simpler sensor, a slightly more complicated software outlook, and you were getting back the same data that you were proposing to do by choking off the instrument, and you'd be getting the enhanced quality data anyway, with the agent-based system. So from an agent-based viewpoint, any sort of science question that you could put together as a set of recognizers and then a set of rules that you could follow from what you're recognizing, you could put that encapsulate that in an agent and have that running on board the spacecraft and actually do some prioritization of the bits that you're collecting.
Excellent.
So I've already given you hundreds of agents with that particular example.
Thank you. And another one is in the slide you had, which separated the automation of the space segment and the ground segment. If we can focus on the space segment, you have worded it as a community of agents. Can you elaborate a little bit on that, please?
I'll just bring that back up over here.
Okay.
Can you see that?
Not yet. Oh, yes.
Okay. Yeah, one of the things that people looked at in the agent-based research was the interaction between different agents. That was an important part of that work, because you had a number of different agents, each one tasked with a particular goal, and they may be using shared resources. So a lot of the work, and particularly the work done by Walt Truskowski, who was very interested in how agents interact, would speak of agent communities where you would start an agent would begin its life or migrate into a particular environment where there would be other agents around, and these agents would be able to interact with each other. And some agents would be providing different services, like you might have an agent that's running communications, another agent that's running an imager, another agent that's running a particular a spectrograph, and then in order for each of these agents would be operating the spacecraft instruments, collecting bits, moving the spacecraft around, and then you'd have, for example, the goal-based agents that were trying to satisfy science goals. and then this community of agents would be sending requests and plans and demands back and forth amongst them, with some degree more or less of communication. And that was a big drive, was to figure out how do these agents have to behave so that you would actually have a coherent and resilient group behavior for the entire community as a whole. And that realization was one of the things that led Steve Curtis and myself and Pamela Clark to start to look into how you discipline these guys and how you integrate them, and led us to the neural basis function concept, where you had a neural basis function which, in analogy with, say, a basis function from mathematical physics, is associated with a particular behavior, and then you compose these different behaviors to get the overall behavior of the system. So, and there are certain rules for what a neural basis function is, how it evolves, how it behaves, and how you connect it with the others into a synthetic neural system, which I suppose would be the analogy to the agent communities. So with the agents, you have a number of different agents, each pursuing their own goals, providing different services, and they're interacting with each other, and that was the foundation of the agent community. And again, how to make that coherent and stable was a big question for agent-based research.
So, if I can say, the agents in the spacecraft are in the space segment versus the agents in the ground segment, they all have different behavioral characteristics in terms of dealing with time or the type of messages. Or your attempt included characterizing all agents to be same or different or classified? Help, please.
Well, Truskowski's vision was essentially to provide a distributed agent environment where you could have an agent migrate from one place to another. So you could have an agent start out its life, if you will, in the user-developer sandbox. You know, your team of scientists working on the ground, trying to put their goals and science recognizers and priorities into that one particular consumer agent. And then the idea then was that, okay, once you have that agent developed at that level, then to move it away out of the sandbox, say move it into the operational environment, either on the ground or eventually up into space as well. So you could have these agents representing different tasks and have them move inside this distributed agent environment pretty seamlessly. So that was the vision that he was hoping to work for, or work towards.
Okay, help me here. Now, if we stretch this concept of agent, and we remember we had another presentation about the lunar networks implemented on the surface of the moon, which probably will be handling a fleet of vehicles, rovers, and robots, and excavation equipments, etc.
Right.
So these type of approach to agents will also work in that environment, particularly in selectively taking a person, a human, to replace a agent. Would that be within the scope of your agent definition?
In essence, yes.
So, in case some of the rovers are driven within the standard scope of automation, they will get around by themselves. But they encountered a situation that was not programmed for, or the agents on board do not know how to deal with it. Such a situation can be handled by a human on ground, like going around pebble or a pit and things like that was my thinking.
Yes, yes, that is that is a that's a reasonable interpretation, sure. One of the things that runs into that goes back into that human in the loop problem, the 99% autonomy solution. So, whenever you have, so one of the barriers to having autonomous systems right now is that, okay, you think that you've caught all the contingencies, but you're never quite sure, and then you're worried. And so you start to engineer your system so that people have access to it, or people have a lot of access to it, or people actually essentially control the thing, except for some very minor, very predictable aspects of the system behavior. And that's essentially where we are right now. And really, because we have a big dependency on people, you are not able to. There are parts of the space environment that we're not able to access. And for example, if you had something that could land in rough terrain, on Mars, you could actually have the thing land on the top of that mountain that the Mars rover's Curiosity is currently at the base of, and has taken such a long time to go from the flat, safe, regular landing place over to where it's getting kind of rough and rugged and a little bit harder to pick your way through. So
interesting.
That 99% is a big issue, and again, like I said before, that's been the problem with some of our cockpit aviation recently, and some of the big accidents that we had, like the airliner that crashed over in California, on the runway. They didn't understand or didn't precisely deal with the automated system that they had, and then when they were in contingent operations, the humans weren't up to actually operating the system properly. So, this is a repeated theme, and something that you really have to take care of. You want to move to something that you have essentially as much confidence in as you would have it with a person. So that's where you're going to have to go with this, particularly with something where you have a lot of remote assets, a lot of remote nodes, and they're going to be doing some pretty complex things, providing each other services, and that's what we're envisioning with the lunar network. Right.
So if you can scroll the image so we see a little bit of the bottom side.
You get the whole picture here.
Yeah. Okay. So let's kind of do the very bottom section, agent development.
Right.
So that was part of the development system. Okay. That makes sense. Okay. All right. So essentially, I think that's all the few things that came across my mind. And where do you think we take this as a next step in the lunar network SIG?
For the lunar network SIG?
Yeah.
There are two big directions or thrusts that you need to pursue for to bring this to start to address these questions of autonomy to the Cube spacecraft environment and the LunarCube environment. One is essentially this notion of agents or agency. Building up the automation, building up a capability for different behaviors to be, say, tested out on the ground, run on the ground in an operational environment, and then having that be transferred and operate in a coherent fashion in the cloud. Can you still hear me? I think I dropped out for a second.
No, you're back. Keep
Okay.
going. Yeah.
Right. So one thrust is this notion of being able to move your agents or agency from one place to another, and that's going to require, essentially, what we're now calling, cloud-based approaches. How do you get, how do you set up the transaction system? How do you get your services running? And the agents will essentially could actually be synonymous with the services at that point. The other thing that needs to be looked at is the disciplining. How do you discipline the different agents? How do you keep bad actors from bad agents, agents that have errors or not working properly? How do you save yourself from them and correct the system?
And when you say bad agents, it's like misbehaved or incompatible or non-responsive.
That's right. Agents that for some reason are not appropriate for the environment. You could have a perfectly good agent that has a particular rule set, and in following those rules causes bad things to happen. So you need to be able to balance off, the authority, the choices that you're delegating to an agent with the rules that it's going to follow. And so that second thrust that I'm talking about is how you actually make the system resilient. How do you get the agents to work together? And from my point of view and the work that I've done, that goes to the synthetic neural system research that we did, where you talk about how to synthesize and integrate different behaviors and have them operate and evolve in a stable way, so that you maintain coherent system behaviors overall. So those are the two ways. Just sort of the baseline. How do you get the behaviors? How do you move behaviors around in the cloud? And then the second one is how you make them stable and resilient and evolve in a coherent and profitable fashion.
Excellent, excellent. That was quite good, and I learned a thing or two from you. And we still have to go quite a bit of ways in the lunar network SIG. So, can you think of a future topic that, in terms of autonomy, human in the loop, and proven agents on higher, like a mission sequence that is able to do under known circumstances, should be able to do it through the missions because of the repeatability and accuracy. And certain times when the parameters around which it's better judged by a human should be able to step in. And that kind of a provisioning system, like this, has to be in a manner that should be able to be provisioned, like in the enterprise system. I would appreciate if we can kind of think of, we can of course discuss offline and later on revisit the subject. It was very nice and thought-provoking. Thank you, Megan.
You're welcome, and thank you. That's an excellent question that you've ended with us. Particularly with how you include people, the human element into the systems that I'm talking about, and that's something that we put some thought into as well. So I look forward to talking about that and at a future discussion.
Okay. Do we have to cover any last thoughts, or we can wind up today's call?
I think I've done enough talking for today.
Okay. Thank you very much. And folks, we're winding up our show today, and please visit, watch this recorded session, and leave comments. we'll get back to you. Thank you.
Been a pleasure.